गुड मॉर्निंग, गुड आफ्टरनून, जिथे जो ग्रीटिंग है एक्सेप्ट करियो। पेज नंबर 243, द क्वांटम स्टेट ऑफ अ पार्टिकल। What kind of picture of physical reality does this provide us with at the quantum level, where different alternative possibilities open to a system must always be able to coexist? Added together with these strange complex number weightings, many physicists find themselves despairing of ever finding such a picture. They claim instead to be happy with the view that quantum theory provides merely a calculational procedure for computing probabilities and not an objective picture of the physical world. Some indeed assert that quantum theory proclaims no objective picture to be possible, at least none which is consistent with physical facts. For my own part, I regard such pessimism as being quite unjustified. In any case, it would be premature, on the basis of what we have discussed so far, to take such a line. Later on, we shall be addressing some of the more striking, puzzling implications of quantum effects, and we shall perhaps begin to appreciate more fully the reasons for their disappear. But for now, let us proceed more optimistically and come to terms with the picture that quantum theory appears to be telling us if we must face up to. This picture is that presented by a quantum state. Let us try to think of a single quantum particle. Classically, a particle is determined by its position in its space, and in order to know what it's going to do next, we also need to know its velocity, or equivalently its momentum. Quantum mechanically, every single position that the particle might have is an alternative available to it. We have seen that all alternatives must somehow be combined together with complex number weightings. This collection of complex weightings describes the quantum state of the particle. It is standard practice in quantum theory to use the Greek letter pronounced as psi for this collection of weightings, regarded as a complex function of position, called the wave function of a particle. For each position x, this wavelength has a specific value denoted psi x, which is the amplitude for the particle to be x. We can use the single letter psi to label the quantum state as a whole. I am taking the view that the physical reality of the particle's location is indeed its quantum state psi. How do we picture the complex function psi? This is a bit hard for all of three-dimensional space at once, so let us simplify a little and suppose that the particle is constrained to lie on a one-dimensional line, say along the x-axis of a standard Cartesian coordinate system. If psi had been a real function, then we could have imagined a y-axis perpendicular to x-axis and plotted the graph of psi. However, here we need a complex y-axis which would be an Argand plane in order to describe the value of a complex function psi. For this, in our imagination, we can use two other spatial dimensions, say the y direction in space as the real direction of this Argand plane and the z direction as the imaginary axis. For an accurate picture of the wave function, we can plot psi of x as a point in this Argand plane, that is in the yz plane, through each position on the x-axis. As x varies, this point varies too, and its path describes a curve in space without finding about in the neighborhood of x-axis. Let us call this curve the psi curve of a particle. The probability of finding the particle at a particular point x, if a particular detector were to be placed at that point, is obtained by forming the squared modules of the amplitude, which is the square of the distance of psi curve from the x-axis. To form a complete picture of this kind for the wave function throughout all of the three-dimensional physical space, 5 dimensions would be necessary, 3 dimensions for physical space plus another 2 for the Argand plane at each point in which to plot psi of x. However, our simplified picture is still helpful If we choose to examine the behavior of the wave function along any particular line in physical space, we can do so simply by taking our x-axis along that line and provisionally using the other two spatial directions as providing the required Argand planes. This would prove useful in our understanding of two-slit experiment. As I mentioned above, in classical physics, one needs to know the velocity of a particle in order to determine what it is going to do next. Here, the quantum mechanics provide us with a remarkable economy. The wave function psi already contains the various amplitudes for the different possible momenta. Same disgruntled readers may be thinking that it is about time for a bit of economy, considering how much we have had to complicate the simple classical picture of a point particle, though I have a good deal of sympathy for such readers. I should warn them to take eagerly what morsels are thrown to them, for there is worse to come. How is it that the velocity amplitudes are determined by psi? Actually, it is better to think of momentum amplitudes. Recall that momentum is velocity multiplied by the mass of the particle. What one does is to apply what is called harmonic analysis to this function psi. It would be out of place for me to explain this in detail here, but it is closely related to what one does with musical sounds. Any waveform can be split up as a sum of different harmonics, hence the term harmonic analysis, which are the pure tones of different pitches. In the case of a wave function psi, the pure tones correspond to different possible momentum values that the particle might have, and the size of each pure tone contribution to psi provides the amplitude for that momentum value. The pure tones themselves are referred to as momentum states. What does a momentum state look like as a psi curve? It looks like a corkscrew, for which the official mathematical name is a helix. Those corkscrews that are tightly wound correspond to large momenta, and those that wind hardly at all give very small momenta. There is a limiting case for which it does not wind at all, and the psi curve is a straight line. The case of a zero momentum. The famous Planck relation is implicit in this. Tightly wound means short wavelength and high frequency, and hence high momentum and high energy, and loosely wound means low frequency and low energy, the energy E always being in proportional to the frequency. If the Argand planes are oriented in the normal way, then the momenta which point positively in the direction of x-axis correspond to the right-handed corkscrews. Sometimes it is helpful to describe quantum states not in terms of ordinary wave functions as was done above, but in terms of a wave function of momentum. This amounts to considering the decomposition of psi in terms of various momentum states and constructing a new function psi naught or psi tilde, this time a function of momentum p rather than a position x, whose value psi of tilde p for each p gives the size of the contribution of p momentum state to psi. The space of ps is called momentum space. The interpretation of psi is that for each particular choice of p, the complex number psi p gives the amplitude for the particle to have a momentum of p. There is a mathematical name for the relationship between the functions psi and psi tilde. These functions are called Fourier transforms of one another. After the French engineer mathematician Joseph Fourier, I shall make only a few comments about this relationship here. The first point is that there is a remarkable symmetry between psi and psi tilde. To get back to psi tilde from psi or psi to psi tilde, we apply effectively the same procedure as we did to get from psi to psi tilde. Now it is psi which is to be subjected to harmonic analysis. The pure tones that the corkscrews in the momentum space picture are now called position states. Each position x determines such a pure tone in a momentum space, and the size of a contribution of this pure tone psi tilde gives the value of psi of x. A position state itself corresponds in the ordinary position space picture to a function psi which is a very sharply peaked at the value of x in question, all the amplitudes being zero except at a x value itself. Such a function is called Dirac delta function, though technically it is not quite a function in ordinary sense, the value of x being infinite. Likewise, the momentum states give delta functions in the momentum space picture. Thus we see that a Fourier transform of a corkscrew is a delta function and vice versa. The position space description is useful whenever one intends to perform a measurement of particles' position, which amounts to doing something which magnifies the effects of a different position particle positions at the classical level. Roughly speaking, photocells and photographic plates affect position measurements for photons. The momentum space description is useful when one proposes to measure the particle's momentum, that is, to magnify the effects of a different possible momenta to the classical level. Recoil effects or diffraction from crystals can be used for momentum measurements. In each case, the squared modulus of the corresponding wave function gives the required probability for the result of a required measurement. Let us end this section by returning once more to two-slit experiment. We have learned that according to quantum mechanics, even a single particle must behave like a wave at all. By itself, the wave is described by the function psi. The most wave-like waves are the momentum states. In this two-slit experiment, we envisaged photons of a definite frequency, so the photon wave function is composed of momentum states in different directions, in which the distance between one corkscrew turns and the next is the same for all the corkscrews, and the distance being the wavelength. The wavelength is fixed by the frequency. Each photon wave function spreads out initially from the source S, and no detection being made at the slits. It passes through both slits on its way to the screen. Only a small part of this wave function emerges from the slits. However, we think of each slit as acting as a new source from which the wave function separately spreads. These two portions of wave function interfere with one another so that when they reach the screen, there are places where the two portions add up and places where they cancel out. To find out where the waves add and where they cancel, we take some point P on the screen and examine the straight lines to P from each of the two slits T and B. Along the line TP we have a corkscrew, and along the line BP we have another corkscrew. We also have corkscrews along the lines ST and SB, but if we assume that the source is the same distance from each of the slits, then at the slits the corkscrews will have turned by the same amounts. Now the amounts by which the corkscrews will have turned by the time they reach the screen at P will depend upon the lengths of the lines of TP and BP. When these lengths differ by an integer number of wavelengths, then at P the corkscrews will both be displaced in the same direction from their axis, that is theta is equal to 0, where theta is in a previous section. So the respective amplitudes will add up and will get the bright spot. When these lengths differ by an integer number of wavelengths plus a half of wavelength, then at P the corkscrew will both be displaced in the opposite direction from their axis, that is theta is equal to 180 degree. So the respective amplitudes will cancel and we get a dark spot. In all other cases, there will be some angle between the displacements of the corkscrews when they reach P, so the amplitudes add in some intermediate way and we get a region of intermediate intensity. Next topic is uncertainty principle, and I'm going to read it tomorrow. Thank you.